Frank Dipp, who comes from the University of Waterloo, where he's a chaired professor. Frank has been working on software engineering and program analysis for many years. Before coming to Waterloo, he was at IBM, where he managed. Frank and I have worked together on a number of occasions, and this is actually a collaboration. So thank you, Frank.
Thank you, Jan. Back here at Purdue. What I'm going to be talking about today is a topic that we call data-centric synchronization. And this is joint work in addition to Jan and Mandana Vaziri. And this is really a talk about a language design project where the goal is to improve the state of the art in how to program concurrent systems. Moore's law, as you all are probably familiar with, there's a number of different formulations, but the most common one seems to be that transistor density doubles roughly every 2 years. And for a long time, this increase in processing power came in the form of increased clock rates and instruction level parallelism, and that was really great because you could take an existing program and it would just run faster year after year, and everything was wonderful. More recently, in the last 5 or 10 years or so, the increased chip. And now things have changed because to take advantage of that, you have to write your program in a multi-threaded way. So the starting point for this work is concurrent object-oriented programming, as in Java, for example. The basic model is you have a number of threads. They execute concurrently. They operate on shared memory. And if you want to constrain the order in which organization by introducing locks in your program. The problem with this model, as I will argue, is that it's a highly error-prone programming model because programmers have to really think very carefully about when and to acquire locks and release them. And if they make mistakes, then a number of concurrency-related errors might occur, such as data races, atomicity violations, and even deadlock. And that's what the goal of our research has been. So in our approach, which we call data-centric synchronization, the approach is more declarative than in traditional approaches. And by this I mean that you specify your synchronization constraints declaratively when you declare your data, rather than trying to specifying your concurrent by encapsulating them in lock acquires and releases. I will talk briefly about some semantic guarantees that are provided by our model, and then I'll present an experimental evaluation where we took some existing concurrent Java programs, rewrote them in our own language, which is called AJ, which is short for Atomic Java. And I'll show you how our amount of effort required by programmers to specify the synchronization constraints. And I will also talk about the performance evaluation we did. Okay, just a few words about shared memory concurrency. So the idea is very simple. You have a number of threads or cores or CPUs accessing a common pool of memory locations. There's no explicit communication primitive you want. And if you want to impose some constraints on the order in which threads operate on these locations, you insert synchronization operations, which is basically a lock acquire and lock release in the setting of Java. The purpose of concurrency control is to restrict the number of interleavings of threads that can occur. And the purpose of this is to prevent undesirable schedules that may result in errors, violations, or even deadlock if your program is over-synchronized. And in traditional object-oriented languages, you basically do that by acquiring locks, as I mentioned. And this is done with the synchronization, the synchronized keyword that you may be familiar with from Java. So let me go through a few examples to illustrate the kinds of problems in Java. So what you see here is a simple class counter. It has a single field called count, which is initialized to 0. And there's a method add where you read the current value of the counter, you add the argument of this method add to it, and then you store it back into the count field. So now let's counter object, which is done by a thread T0, and then we spawn off two threads, T1 and T2, where T1 is trying to add the value 2 to the counter, and T2 is trying to add the value 3 to the counter. So there's a number of ways in which to schedule T1 before T2. So then you initialize the count variable to 0. T1 comes along, it reads 0, it adds 2 to it, and it stores it back into count. So count now has the value 2. And then the same thing happens for the result is the value 5. There's, of course, a schedule where the second thread goes first and the first thread goes next. If you work through the arithmetic here, you would get the same result, and you would, again, compute the value 5. Up with a scheduling of the two threads where their instructions are interleaved, something more interesting happens. So let's look at this in a little bit of detail. Thread 1 comes along and adds 2 to it, so we store that value in the local variable temp that was declared in the method. Now the second thread comes along. The count field in the object hasn't been updated yet. It stores it into its local variable temp. And now the threads continue to store back the value that they have computed. And the end result is a value 3, which is not what you would expect when you're adding 2 plus 3. The problem here is that the calls to the add method are not executed atomically. And this is an instance of a situation that is known as a data race, which is usually defined as two threads concurrently accessing a shared location where one of these operations is a write operation, and where there's no synchronization. So there's a number of ways you can prevent data races like the one I've shown you. The mechanism in Java for doing that is by synchronizing on a lock object. So here you can see how you can modify the class to kind of the class where assigning a new object into a field called lock. And then when we execute the add method, we're synchronizing on the lock object. And this guarantees that only one thread at a time field is being manipulated. And as a result, you would no longer have the data race. It would no longer be possible. So there's a number of common idioms I want to just briefly show you. So instead of explicitly allocating a lock object on which you've invoked the method, and you can do that by synchronizing on the this reference, which is referring to the object on which the method was invoked. And this would basically have the equivalent effect of preventing the undesirable schedule from happening. And for synchronizing on this, you can simply put the synchronized keyword on the method itself, which would have the effect of surrounding the body of that method with synchronized on this. And this would again have the same effect of preventing the undesirable schedule from happening. Things get a little bit more interesting when you operating on multiple locations at once. And what I'm showing you here is an example from the Java standard collections library, the class vector in there, which is an array-based implementation of a vector. And what I'm showing you here is currently declared in the libraries. And this is a constructor that takes as an argument a collection C from which it will initialize the vector. So the end result of this operation you would expect to be a vector that contains the same elements as the argument collection C that you passed in. So let's look at a situation where the argument collection contains 3 elements, A, B, and C. And now we're concurrently executing 2 operations. The first thread is going to create a new vector with the same arguments as C by calling new vector. And the second thread is concurrently going to clear the elements of the vector C, the argument collection. So what you can see is going to happen then is we can start executing the vector, the constructor of vector. And at this point, the field element count will be 0, is null, and the argument collection C is containing A, B, and C. We can execute the first statement. This will update the element count of the field of the vector object that we're operating on to be 3, which is the size of the arguments collection that we're passing in. The next instruction will contain 3 null values. And what might happen now is that thread T2 could now start executing and clear the argument collection. And at this point, the C argument collection would contain T1 were to continue the call to the toArray method here, which would have the effect of copying elements from the argument collection into C, would have no effect. So the end result of doing these 2 operations concurrently would be a vector containing 3 null values, which is probably not what you expect when you try to initialize a vector entirely or not at all. And this is an example of what is called an atomicity violation. And the issue with an atomicity violation is you're operating on multiple values, and because you're not executing the operation atomically, data corruption, And in some other examples, like the one I'm showing you here, I'm not showing you all the code, but there's a similar issue with the add-all method in vector, which also takes an argument collection. There, if the argument collection is concurrent, which is never the desired outcome of any execution, I would argue. Okay, so you can prevent atomicity violations like the one I've just shown you, again, by introducing that you do not want to perform these operations until you know that nobody else is operating on either of these collections. And you can do that by synchronizing on both the current argument, the current as well as the argument collection. So you could have two synchronization operations at this point, and this would ensure that the body of this method is only going to be executed by someone who has a lock on both of these objects, and that would prevent atomicity violations. Of course, this is risky, because if you have multiple threads and multiple locks, there's a chance that these locks might be acquired out of order. And just to show you an example of what might happen, there's v1 and v2, and I'm trying to concurrently execute v1.addAll v2 and also v2.addAll v1, I might get a situation where each of the threads acquires the lock for one of these objects, a deadlock situation. So at this point, I think we've seen the three major sources of concurrency-related errors in concurrent object-oriented programming with Java with locks, which is data race. So there's a number of ways to prevent deadlock. I just want to sort of give the high-level approaches that people typically take. There's a number of specialized notions of locks, which you can use in Java using the library, which is providing concurrency-related data structures. And it provides a special kind of lock called a Reentrant Lock, and it has special features. In particular, it has a feature called try lock, which lets you atomically try to acquire a lock or return false if the acquire operation doesn't succeed. So you acquire lock 1, you could do the try lock on the second lock. If you get it, you're good. You can continue because you have both locks and you will not get a concurrency violation. If you're unable to get the second lock, you can release the first one and go back to step 1. And that would, after you try this long body of this method, if there's a notion of fairness. So try locks are slower, reentrant locks are slower than regular locks. So this is in general not the most desirable approach of preventing deadlock in concurrent object-oriented programs. So a better on your lock objects and then ensure that you only acquire locks in accordance with that order. If you do that, you can guarantee that there will be no deadlock. The problem with establishing lock ordering is that it's often the case that the objects on which you want to acquire locks are allocated to establish a static ordering on these objects. Either way, I would argue that if you go with one of these approaches, the code that you write to avoid these concurrency-related errors is going to be more convoluted, uglier, and in all cases, the burden is on the programmer to get it right. So this was basically what motivated us to try to come up with a better way of programming concurrent object-oriented systems. So just to recap, preventing concurrency-related errors. If you are accessing shared locations, you should protect them with locks to prevent data races. If you're operating on multiple locations, you have to be careful to avoid atomicity violations. And you have to acquire multiple locks in a consistent order to prevent deadlock. And it's important for program locations whenever they want to avoid these kinds of problems. If you just forget one, you run the risk of encountering data races or atomicity violations. So there's been a lot of work in the literature on dealing with concurrency-related errors. I don't have time to go into this in a lot of detail. I just want to sort of point out the major areas. There's been a lot of work on doing static program analysis. Here the objective is to reason about all possible executions of a program and either to detect deadlock, atomicity violations, or data races. There's work on dynamic analysis, where the objective is to study a specific execution of a program and determine if there's data races or atomicity violations in that particular execution. And in some cases, dynamic analyses can even reason about other executions that are similar to the one that you observed. There's type systems where there are additional annotations on program constructs in your source code. Check type correct according to the type system. There can be a guarantee in such systems that your program will not deadlock or it will not have data races or atomicity violations. There's more heavy-duty static approaches for reasoning about deadlock and other problems related to concurrency that rely on theorem proving and verification. And there's been, of course, approaches that are more focused on changing the language design itself. And here, actually, basically provide programmers with a higher level mechanism for specifying concurrency constraints. And the one in the middle is probably the closest to what I'm going to be talking about next. So our approach is called Data-Centric Synchronization. And the goal of this work is really to raise the level of abstraction in concurrent object-oriented programming. And we do this by specifying synchronization constraints declaratively when you declare your data. And given that we're doing this work in the context of Java, you should think of this as specifying synchronization constraints on fields in classes. We do this using a language construct called an atomic set, which is a set of fields in an object on which a program should operate atomically. And the main, an important characteristic of our approach is that it's intended to be compositional in the sense that we want to make it easy to build larger synchronized data structures out of smaller ones. And I will talk briefly about the correctness guarantee that we can give you when you write your programs using our system. So this is implemented in a language called AJ, which is short for Java with atomic sets. And I will talk about an evaluation where we measure annotation overhead, which is the number of synchronized keywords or consumer has to write about a performance experiment as well. Just to say a few words about terminology. So here I'm showing you a simple class bank account, which has fields checking and savings and transfer counts. And let's assume that we have a method transfer here, which takes some accounts. And this transfer method also operates on this transfer count field, which keeps track of how many transactions you have performed, perhaps. So in this case, you can see there's a set of locations on which the method operates and where it's desirable to maintain the consistency between these two fields. In particular, we do not want to ask your checking account, but not yet deposited in your savings account. And in Java, this is done with the synchronized keyword. We surrounded the block of code that operates on these fields with a lock on this. In our setting, the set of locations on which a method like this operates is called an atomic set. So this is the set of fields that we have that share a consistency property. And the regions of code that are intended to preserve the consistency of atomic sets we call units of work. And these are, in our setting, identified with methods in a class. So we've gone for a fairly close integration with the language constructs that are already there in Java. And the goal of units of work is, well, what their property is they will preserve the consistency of the atomic sets on which they operate. And I think that's what I want to say about terminology at this point. So language constructs in AJ. I'm showing you here a somewhat smaller example, a counter class again. You can see there's a single field in this class called val. And we've declared an atomic set A, which is on how this val field is going to be operated on. So the construct is basically an atomic set which is declared inside of the class. And then to put a field in an atomic set, we put the modifier atomic A on that field. All the methods that operate on the val field, which is in the atomic set A, are by default units of work for this class. So this will have the effect of making the get, stack, and inc methods in this class operate atomically on the val field. So we will not, for example, expose intermediate states where dec has read the old value of val, decremented it, but where it has not yet written out that value, so the field. One further comment I want to make on this example is that each instance of a class will have its own instance of the atomic set. So if you have multiple counter objects, they will each have their own instance of the atomic set A. In some cases, it's desirable for a single method to operate on multiple atomic sets as a union. For example, think of a transfer where you want to take some money out of one counter or a number out of one counter and you want to add it to another. It may be desirable to not expose an intermediate state where you have decremented one but not yet incremented the other. This is possible in our approach by specifying that this method is a unit of weight. You can see the way to achieve that is to place a unit 4 modifier on each of these fields. And this will have the effect of making this method a unit of work for the combined atomic set containing the elements of each of the atomic sets of the arguments of the method.
On that previous slide,
Yep.
Is A here an atomic set in counter or an atomic set in T?
You should read this as transfer is a unit of work for atomic set A in counter. We've tried to make that a little bit visible in the syntax. Okay, so then another construct we have is for building larger atomic sets out of smaller ones, has to do with situations where you want to build a larger synchronized object out of smaller ones. So here, let's say we have a pair counter, which is a pair of counters, and let's say we have a method that operates on both of these counters, like inc high here. In this case, what we would like to construct is a single atomic set that contains the local state in this pair counter object, which is the diff field in this case, as well as all the fields in the atomic sets of the two counter objects that are pointed to by the low and the height fields. And first we declare a new atomic set in the pair counter class. We call that B, and we can see we store all of the fields in that class in this atomic set pair count, B for pair counter. And then we have something called an alias annotation on each of the counter variables, fields that are used in this class. And the way to read this A equals this.B is that the atomic set A in the counter pointed to by the field low is unified by the atomic set B in the pair counter object that is pointed to by this. So the syntax is a little bit verbose, but this combined syntax here will have the effect of creating a single pair counter object, a pair counter object that has an atomic set that is basically merged with the atomic sets of the two counter objects that it contains. So this will let us build larger data structures that are synchronized with an atomic set of the constituent objects that it's built out of. So those are basically the main constructs. We have some additional constructs that you can read about in our papers if you're interested. So we have some support for barrier synchronization. There's an atomic set version of wait and notify. We have a notion in some cases where you cannot use the static type that has the atomic set declared in it, like in an equals method. We have a mechanism that is sort of in spirit of downcasting to recover that information. There's a notion of declaring a class to be internal. In this case, that would have the effect of forcing the atomic sets declared in that class to always be aliased with the atomic set of another. And that's used in a case where you have an object that is owned by a larger data structure. Think of the entries in a linked list, for example. We have some mechanisms for performance tuning. You can declare a method to be not a unit of work for specific atomic sets using a not unit for construct. And then there's lastly a notion of ordering annotations, which can be used by an analysis that can guarantee the absence of deadlock. So, yes?
Can you just go back a few slides for where you showed one before this maybe?
This one here?
Yeah. Now this annotation here, when you define, is that the onus is on the programmer to add that? So isn't that essentially similar to having the onus on the user to put synchronize at the right places? Could they not do that and get away with it?
It depends on how they've structured their application. If they structured their application in a different way, where the transfer method would be on the same class where the atomic set A is to put the unit of work on the disk pointer. Basically, what we've done is we've chosen a default for units of work for an atomic set. And the default we've chosen is all the non-private methods in the class declaring the atomic set and the subclasses of that class.
But the usual challenge is when you've got a client class using that, and then they use it in a manner that is not, protecting the concurrency. It's sloppy.
But I think in our approach, you will find that the client often doesn't need to use a lot of annotations for dealing with concurrency. I mean, I think there are cases where if you have a method that operates an atomic set of the object in its declarant class and it has an argument that also was showing you at the beginning of the talk, then you have to use, in our approach, a unit of work annotation on the arguments. I suppose we could have chosen a different default. We could have, for example, chosen to always have methods be a unit of work for arguments if there are units of work declared in that class. I think the approach we've taken, I don't know, it's one possible option. There's different options one could take. But in the end, mechanism to specify what are the units of work for an atomic set. And we've chosen one and we've given you mechanisms for overriding the defaults. Maybe another approach works better in certain scenarios. Yes?
I have a similar question. So when you're combining atomic sets in the, was it pair counter example, by taking the atomic sets of the individual counters, and you're composing that way, aren't you somehow violating encapsulation? When you know classes, right? In the pair counter class, you need to know what the atomic sets in the counter class are, and possibly you need to know what attributes or what fields in the counter class are in what atomic set, because depending on which methods you invoke in that class, you need to know which atomic sets those are using or which fields, or is that all hidden?
No, I think that's a fair use, this aliasing mechanism. It tends to be for in situations where you already have to know enough. I mean, you have to know information about the object that you're building yourself out of. I will show in a moment an example of aliasing as we encountered that we needed it when we created a thread-safe version of the Java collections. It was being constructed and it uses a hash map. And it needs to know that there is an atomic set in the hash map that it's using to implement itself. But other than that, it makes it really easy to build a larger, properly synchronized data structure out of a smaller one. So I think it's a reasonable. Are there any more questions at this point? Then let me just go on. We can take more questions as needed, of course. Okay, so we formalized this approach for a core subset of the AJ language using an extension of featherweight Java. You can think of this formalization as supporting Java types with optional alias and internal annotations. And we have some constraints on these annotations to make sure that they are properly preserved by assignments and other language constructs and subtyping. The correctness guarantee that we guarantee is that for each atomic set R, the units of work for that atomic set will happen in a serial order. And I have some examples coming up to illustrate what that means. And this is a generalization of an existing notion from database theory called conflict serializability. Okay, so here's some discussion of this notion of atomic set serializability. So this is basically defining if you have a program with atomic set annotations, what are the interleavings that are allowed when you try to execute concurrently have multiple threads that execute on the same, on methods that operate on the same atomic set. So here's a scenario with two threads, T1 and T2. Let's say there's two atomic sets, A and B, where the first one contains two fields, C and S. You can think of those as check will, element O, which could be a counter of the number of operations performed. And let's say we have two threads, and the first one tries to execute a read on the field C, a write on the field C, a read on the field O, and so on and so forth. And you can see that I've indicated with these brackets here how these operations are grouped in terms of units of work executed by the multiple threads. And units of work can be nested in cases where you have methods operating on one atomic set, calling other methods on either the same atomic set or different atomic sets. So that's how you get this nesting. So given this scenario, the question is, what kinds of interleavings are allowed under our model? Well, two executions that are definitely allowed are that are executed before all the operations performed by the other thread. So these are trivially allowed by our model. Another execution that is allowed in our model is the following. So here you can see that some operations executed by thread 1 are executed, then thread 2 executed read of O and write of O, and then thread 1 continues and it executes the remainder of the operations. And why is this allowed? Well, this is an atomic set serializable sequence of operations, because if you project these operations onto each atomic set, then you will get, from the projection of the first one, you will get a sequence of operations that all originate from one unit of work. So that's by definition serial. And if you look at the second sequence, if you project on the atomic set B containing the field O, you will see that the operations you get come from each unit of come from the units of work from different threads in serial order. You have T1, then T2, and then T1 again. So this is a legal execution. Here's an example of an execution that is not legal, because if you were to project this onto the second atomic set, operations from different threads are interleaved. So this would not be allowed by our system, and our compiler would not generate code ever where something like this could happen. Okay, so we've implemented, yes?
So one of the assumptions with complete serializability is the only way in which multiple threads affect each other. But in a program, you could have leakage of data from one field to another because they've been copied to some other value, or maybe there's aliasing going on. So would you have to check for all those cases, and would that be a significant overhead?
I think in cases like that, it's really the burden. Well, let me think about that for 1 second. If you copy an object into another variable, and then you call a method on that other variable, which is really the only way you can operate on fields, because fields have to be private in our model, then it would really not change anything, because you would still execute the same methods, and our compiler would have generated appropriate synchronization code in these methods to make sure that atomic synchronization set serializability is preserved.
Well, what if you just used a method to get a value out, passed it on to some other, copied into some other field, and then that gets later on reused in an execution, which essentially is a form of leakage. Is that outside the guarantee model here, or?
I would have to look at a specific example, ensure that these additional methods that do the copying are units of work on both of the on the atomic set. But we can talk about a specific example. So we've implemented this language design as an extension of Java using the Eclipse programming environment, and also the WALA program analysis framework that was developed by my colleagues at IBM. There are some limitations on our implementation. In particular, it doesn't deal with certain Java language features, such as generics and inner classes. There's no fundamental reasons why one couldn't handle that. It was just more work than we had the cycles for at the time. So what we did is, on our benchmark, there were not really that many uses of these features. We just manually transformed the code to eliminate these. I don't believe this has had any significant effect on our experiments. We translate AJ programs into code that uses standard synchronized blocks. We introduce a lock ordering to prevent trivial cases of deadlock. For example, the case where you have a method that is a unit of work calling another method that is a unit of work. In that case, that you know that the second method doesn't need to do synchronization again because you already hold the lock. So we generate two versions of each method to deal with cases like that, so we can generate more efficient code. I think that's as much as I have to say about the implementation at this point. We did evaluation where we of multi-threaded Java programs, to a large extent programs that had been used by other researchers who worked on analysis of concurrent systems. We also took SpecJBB, which is a well-known performance benchmark, which we will use to measure the performance of our approach. We manually refactored these Java programs into AJ, which was a somewhat painful but necessary job to be able to do the experiment here. And we translated that code into AJ. We translated the AJ code into Java code to execute it to measure the performance. I'm going to talk about two evaluations we count the number of AJ constructs that are needed for synchronization and compare that to the number of synchronized blocks that were present in the original Java code. And this hopefully will give some indication of how much programmer effort is involved to obtain a properly synchronized program in each of the approaches. And performance, we're just going to measure the running time of SpecJBB, meaning both the Java version and several AJ versions that I'll talk about in a moment. So one of the programs that we considered is a significant part of the Java collections framework. I'm just showing you part of the class hierarchy for some of the collections that we modified. So they include some non-trivial classes such as array list, linked list, hash set, linked hash set, which is a special version of hash set, sorted set, and many others. Basically created a synchronized version of these collections that would prevent atomicity violations like the case I was showing you early in the talk with the vector constructor example. It looked pretty similar for all of these collection classes. So what we did is we introduced an atomic set in the root of the class hierarchy in the interface collection on methods such as add all and the constructor of vector that operate on multiple objects that contain atomic sets. We had to introduce our unit 4 annotations because these would not by default be units of work for both. Built a data structure such as a linked list out of smaller data structures like an entry in a linked list. We relied on our aliasing mechanism to ensure that in this case the entire backbone of the list was protected by a single lock. And we did similar things in the map hierarchy. So it's again introducing an atomic set at the root of the hierarchy. We put all the fields in the class in that atomic set. And in some cases, we had to introduce aliasing and unit 4 annotations to get the desired synchronization behavior. The compositionality is something I already mentioned when I was answering Patrick's question. So a typical example, I think, of building a larger data structure out of a smaller one is where you built a hash map out of a hash set. And this illustrates how you can get some form of reuse of synchronization behavior in AJ. So you can do something like create a new hash map object in your client application. And this would be a hash map that knows how to handle its own synchronization to ensure consistency. You can also hash map whose atomic set is aliased to the atomic set of its owner. And in that case, you will get a larger synchronized data structure that is sharing its synchronization with the object that it's building itself out of. So this is, I think, an interesting example of illustrating how you can build larger synchronized structures out of smaller ones in our approach. What I'm showing you on this table here is the number of synchronization-related annotations in 2 approaches for a number of programs. So at the top, you can see the collections framework I was just mentioning, which is about 11,000 lines of Java code. The original version was unsynchronized. I mean, these are all unsynchronized collections that we've looked at. And to make it a properly synchronized framework, in this case, 428, most of which are aliasing annotations, because there tend to be a lot of auxiliary data structures when you deal with collections and iterators. The other programs are mostly programs used by other researchers in the area. You can see they range from 600 lines of code to about 17,000 lines of code. You can see in the second column of the table here how many synchronized keywords were present in the original version. Like in Seawolf here, you can see there were 14 synchronized keywords. And the last column of the table shows the number of AJ constructs. So you can see that in all cases, I should point out, this number is lower than it is in the original Java version. So I think this gives us the amount of properly synchronized applications that do not have data races and atomicity violations and so on is actually lower than it is the case with synchronized keywords in Java. So for the performance experiment, we took SpecJBB, which is a convenient benchmark because it tends to measure its own performance. It has a measure of throughput that it will report when you execute the program. It's a program that simulates a server-side order processing benchmark, so it has how and we converted this program from Java into AJ like we did with all the others. In the course of doing that, we encountered several cases where synchronization seemed to be either redundant or inconsistent, where we would see fields in an object that were playing a very similar role, but where one was synchronized upon and the other one was not. And in our conversion to AJ, we of course we obtained a properly synchronized version. We found an interesting case of where we could use our aliasing mechanism. We found there's a class tree map data storage in SpecJBB, which is a tree map of the classes in the collections that we converted to AJ from Java. And we created a number of different versions of SpecJBB. We started by a naive translation where we simply took all the classes that had synchronization in them in the Java version, introduced an atomic set, and placed all the fields in these classes into the atomic set. That's roughly how we obtained a naive version of SpecJBB. When we did our performance measurements, we found that this did not really scale to a large number of threads, so we started looking into this a little bit to understand what was going on, and we performed some looked carefully at the use of fields in these classes, and in cases where we could see that from looking at the code that a field was basically a read-only field, we would omit these fields from the atomic sets, and that's how we obtained a second version, which we call basic, which is performed slightly better than the original version. And then the last version of SpecJBB, when we found that the performance was still not very similar to the Java version, we obtained by looking more carefully at the use of fields. And we found that there were some scenarios where fields were being operated on that became read-only after a while. And by carefully looking at the code, we could actually improve performance by specifying that certain methods were not a unit of work for an atomic set after understanding that at this point. So I think in general the approach was there, go for correctness first, and then when performance is not good enough, then try to tune the performance by making your atomic set smaller and reducing the number of units of work. So this is actually taken on a machine here at Purdue. It's a machine with 108 cores, of which about 10, of which the last 10 I think are set aside for operating system purposes. So we've basically charted here the throughput of the SpecJBB benchmark as a function of the number of cores, and we go up to 98 cores. The red line here is the performance of the original Java version. You can see that it scales fairly linearly with the number of cores. The green line at the bottom is our basic AJ version. You can see it scales well to about maybe 20 threads, and then performance starts leveling off because it has more synchronization that should be needed, and at some point it really degrades. The black line is the green line is the naive conversion, the black line is the basic, and the blue line is the tuned. You can see basically that with some modest amount we can get performance of our AJ version of SpecJBB that is fairly close to that of the original Java version. And at the same time you can get a performance guarantee, a correctness guarantee that you do not have data races and atomicity violations that you did not have. That's basically what I wanted to report. So I presented a language designed for data-centric synchronization. It provides a correctness guarantee, atomic set serializability, which basically will tell you that you will not have data races or atomicity violations. What I've not talked about, but what we've also done is an reasoning about by establishing an order on atomic sets and making sure that units of work are executed in a consistent order. And I think a key characteristic of our approach is that it's compositional in the sense that it's easy to build larger synchronized data structures out of smaller ones. We have some experience with this language. It seems that annotation overhead compares favorably to AJ constructs in our experiments than you need synchronized blocks in Java. And it seems that acceptable performance is within reach if you're willing to do a modest amount of performance tuning. That's all I have to say. We have a number of publications on this project that I'm listing here, and I'm happy to take more questions. Thank you.
I have a question.
Yep.
So here looking, of course, there is a lot of similarity, and you have this Bernstein reference, which is a little old. So sometimes you want to lock a certain range of values, not explicit objects, but a set of values. Allow new objects to be created within that range or objects to be taken out within that range.
Mhm.
It's called range locking. So, and there are faulty transactions that would result if, or faulty results if such feature is not supported. So I don't know how you compare this with the concurrency in the transaction sense.
Yeah, I would have to think about how you could, if and how you could achieve that with atomic sets. I think it would probably involve restructuring your class in such a way that you could have separate atomic sets protecting only the objects in that range, atomic sets that are separate objects outside of that range. I think that's the best answer I can give you. I don't think the current approach would be a perfect match for scenarios like that. Yep.
So how do you expect your performance to scale with increasing numbers of threads?
That's a very difficult question in general. I mean, we've really only done performance experiments with SpecJBB because it's quite difficult to get your hands on a realistic program that you can run on large machines. And I think it really depends a lot on the structure of your application. I think there are certain scenarios really well. I think the scenario like you see in the Java libraries, I think it's a good match for that. I don't think we have enough experiments done yet to generalize our claims much beyond that at this point. Yeah.
So you mentioned two semantic guarantees with that, right? Serializability and deadlock freedom. There's another one that probably harder, but there's people who have been doing work on this, and I don't know if maybe atomic sets can make it possible to do something like this, which is, how do I know that I've used the right annotations? That I've in order to make sure that the transfer is correct, I need to put those unit 4 annotations in.
Yep.
Do you have any way of sort of analyzing methods that you think that the user thinks are atomic and telling them that yes, you've put the right annotations in there to get the accuracy there?
Before I answer that question, let me mention that there's some work done by someone at the University of Illinois, Peter Dinges. I think what he did is he was analyzing executions of Java programs with synchronized blocks in them and observing which groups of locations were protected by the same lock. And from that, he was inferring atomic sets. And I think his annotations were remarkably similar to the ones that he found. He was using some of our benchmark for that. So in general, the programmer has to understand what he's doing, unfortunately. And I think it's probably easier for a programmer who forgets to include a field in an atomic set to see that he's getting data races than for a programmer who has to deal with low-level synchronized blocks to remember that he has to protect every access to this field. So I think it is somewhat less. It hopefully will show up in ways that are more evident because you either protect all the accesses to a field or none of them. Beyond that, I mean, at some point the programmer just has to know what he's doing. I hope we have given him a better tool with this approach than synchronized blocks.
So when you have a method which shares this unit 4, etc., there may be only small parts of that code that need to actually be locked out. So to
Yep.
speak. Is that the approach that you take, or do you have to lock out the entire piece of code because you've declared it?
Yeah, currently we don't really have very fancy mechanisms for creating smaller units of work. So in the scenario you're sketching, what you would have to do is execute statements into its own method, and then that would become a unit of work.
Couldn't one not automatically see that there's segments of the code where before any initial access, for example, is a simple one to identify where
Yep.
something should not be?
We actually at one point we had an implementation that was trying to be smarter about where to acquire the lock. If you had a region of code before any shared locations were accessed, you could basically postpone the acquisition of the lock until that point. But we found that was actually quite error prone, and at some point we just didn't pursue that fully. But in principle, you can do better than even if your notion is to make the entire method a unit of work for the atomic set, it doesn't mean necessarily that you have to surround the entire dialog.
The performance penalty might come from there.
Ooh, I'm really not sure. It would be an interesting experiment to do. Yep.
Since you mentioned these refactorings, have you run any other kind of software metrics like to verify coupling or cohesion, see whether these refactorings affect the software quality? I mean, just beyond the part of synchronization, right? You talked about the amount of annotations that you require, or otherwise evolve to use or change to use these so user constructs, and does that affect any other aspects of extensibility, maintainability? I mean, there's all these traditional metrics
Sure.
that people run.
I think that's a very good question. For the collections, which are be the biggest example of synchronized data structures that we tackled, I think there were 2 cases where we had to tweak the code slightly to make it fit our model. So it was a remarkably good fit for that. I think for one of our benchmarks, I think we did a somewhat more invasive restructuring because it was using wait and notify constructs that, I don't know, they were not very pleasant to refactor away, but we don't general claims about the impact it would have on code quality overall. My sense is that if you have a well-written framework like the collections, it's really not much of a burden, and it doesn't make things either better or worse. If you have spaghetti code, then I think the burden would probably be negative. I mean, in the sense it would force you to write better code, I would presume.
Okay.
How do we need to handle the security with this transaction model?
I'm sorry,
About the security?
the security. I'm not sure if I understand your question.
Does it violate any of the Java specs regarding the threads?
I don't really think it has anything fundamentally to do with security. I mean, in our approach, instead of writing synchronized blocks on methods, you put a modifier on the fields that are in an atomic set, and from that our compiler generates code that has the same synchronized blocks that you would have before. So I don't think fundamentally anything is different there. I mean, unless I'm misunderstanding your question.
All right, one more?
Is there any time that adding the synchronized modifier on the method itself is better than using this when dealing with a large number of atomic sets? Would it be better than to use only the synchronized function, the synchronized on the function that is dealing with all these sets, other than specifying that it's atomic for every single atomic set?
So my perspective on this is that instead of having to worry about correct synchronization behavior every time you use a shared location, you only have to worry about it once when you declare your synchronization behavior. So I consider it to be an improvement. On the other hand, it does give up some of the flexibility that you may need when you do really low-level synchronization maybe on just parts of data structures. Maybe it's just not a good fit for scenarios like that. I think for general purpose object-oriented programming, I would hope that this is a step in the right direction.